Hello everyone, this is Muhammad Wasim Khan, an instructor for your course Total Quality Management. Welcome to Learn with Wasim. In the previous two lectures, we have discussed Ishikawa's seven basic tools of quality and new seven tools of quality. In today's lecture, we will talk about statistically based quality improvement for variables. In this lecture, we will discuss some of the most important topics like statistical fundamentals. We will also discuss the process control charts with examples. We will discuss some control chart concepts for variables, the process capability for variables, and other statistical techniques in quality management. So let's start with the statistical fundamentals. And while talking about statistical fundamentals, one question must arise or may arise in our mind. And the question is, what is statistical thinking? Statistical thinking is a decision-making skill demonstrated by the ability to draw conclusions based on data. We make a lot of decisions based on intuition and gut feelings. Often we choose friends, homes, and even spouses based on feelings. Therefore, intuition and feelings are very important in making good decisions in certain circumstances. However, intuitive decisions are sometimes biased and wrong-headed. Consider the case of government. Many times it is the most vocal groups that seem to control political agendas. It is difficult for mayors, governors, or presidents to determine exactly what the voting public wants on any issue. As a result, decisions are sometimes made that satisfy the few but irritate the many. Statistical thinking is used, um, in based on these three concepts. The first one is all work occurs in a system of interconnectedness processes. The second one can be all processes have variation. That is, the amount of variations tend to be underestimated. And the third one is understanding variation and reducing variation are important keys to success. Okay, after that, we can have another question. And the question is, why do statistics sometimes fail in the workplace? Before beginning a discussion of statistical quality improvement, we must remember that many times statistical tools do not achieve the desired results. Why is this so? Many firms fail to implement quality control in a substantive way. That is, they prefer a form or substance. We actually provide several reasons as a guide. So you can use this guide to assess whether you or your organization will be successful in using statistics to improve. And some of the reasons for a failure of statistical tools, include the following. I will discuss some of the technical or non-technical, failure reasons for failure of statistical tools here. I will explain only those that may be that I think may difficult for you. Okay, and the rest of them are very simple for you to understand. And the first reason for failure of statistic tool is lack of knowledge about the tools. Usually people don't have, the knowledge about the tools. They even don't know about the tools, or, they may know about the tools, but, they don't know how to use those particular tools. The second one is general disdain for all things, mathematical creates a natural barrier to the use of statistics. Okay, cultural barrier is another main reason within a company that make the use of statistic for continual improvement difficult. Another one can be the statistical specialists have trouble communicating. They have trouble to communicate the statistical thinking and their ideas with managerial generalists. Statistics generally are poorly taught, okay, by the trainers, or emphasize mathematical development rather than application. They just tell them how to mathematically solve the particular problem, but they don't tell the or teach their um, trainees to how to implement those particular solutions to the problem. um, Okay, people can have a poor understanding of the scientific method, and another reason can be organization like patience in collecting data. So all decisions have to be made yesterday. Okay, statistics are viewed as something to buttress an already held opinion rather than a method for informing and improving decision making. Then another reason is that the people fear using statistics because they fear they may violate the critical statistical assumptions. Okay, so they may lack this particular confidence. Okay, time order data are messy and required advanced statistical techniques to be used effectively. Most people do not understand random variation, resulting in too much process tampering. Okay, and I think the last one is that there's a statistical tools often are reactive and focus on effects rather than the root causes. So if the statistical are usually used as a reactive tool, so that can be another problem or reason for the failure of statistical tools. As you can see on the screen, I would like to discuss the type 1 error and type 2 error, but before that, I would like to just give you an idea. Organization like patience in collecting data, all decisions have to be made yesterday. So statistics are viewed as something to buttress an already held opinion. Okay, people don't understand random variation, okay, resulting in too much process tampering. So random variation usually results in in too much process tampering, and the people don't understand that. So statistical tools often are reactive and focus on effects rather than the causes, as I have discussed in the previous uh, slide. Another reason people make mistakes with a statistic is founded in the notions of type 1 and type 2 errors, as you can see on the screen right here. In the study of quality, we call type 1 error the producer's risk, okay? And another one is the type 2 error, and we call the type 2 error a consumer's risk. So type 1 error is a producer's risk, and type 2 error is a consumer risk. And why we call it the producer and consumer risk, I will discuss it with you. Okay. Uh, in this context, producer risk is the probability. Um, Producer risk is actually the probability that a good product will be rejected. So the probability that a good product will be rejected. So that is the producer risk. That is a risk for a producer. Okay, a product producer, for example. And the consumer risk, or the type 2 error, is the probability that a non-conforming product will be available for sale. That is, I would say, it is the probability. A consumer risk is the probability that a non-conforming, or the defective part is available. So that is actually a risk for the consumer, obviously. Okay, so consumer risk happen when statistical quality analysis fails to result in the scraping or reworking of a defective product. When either type 1 or type 2 error occur, erroneous decisions are made relative to the product. So these erroneous decisions can result in a high cost or a lost future sales. Given these problems, we adopt the approach that statistics should be used. They should be used correctly, and they should be, taught correctly. Yeah, so I think, I hope you have understand what actually the type 1 and type 2 errors are, the what are or what are the producers or consumers risk. Let's discuss some understanding the process variation. So we have to understand the process variation here. All processes exhibit variation. uh, you know Actually, there is some variation that we can manage and other variation that we cannot manage. If there is too much variation, process parts will not fit correctly. I'm repeating it. If there is too much variation, process part will not fit correctly, and products will not function properly, obviously, and a firm will gain a reputation for a poor quality. Two types of process variation actually commonly occur. These are the random variation and the non-random variation. So the random and non-random variation are actually the two types of the variations that commonly occur. What is random variation? Random variation is, as I have already discussed with you, but I will explain it more here. Random variation is uncontrollable, and non-random variation has a cause that can be identified. Okay, so random variation is centered around a mean, okay, and occurs with a somewhat consistent amount of dispersion. I'll discuss this in the coming slides. Okay, just listen to it and keep focus on these on my words. This type of the random type of variation cannot be controlled. Hence, we refer to it as uncontrollable variation. And the amount of random variation in a process may be either large or small. When the variation is large, process may not meet specifications on a consistent basis. The statistical tools discussed in in these lectures are not designed to detect random variation. Okay, the statistical tools that actually I'm going to discuss in this lecture are not designed to detect the random variation. Okay, let's look at the figure 12.1, and you can see here, it shows the normal distribution. You can see the normal distribution. The normal distribution. There are three sample variations, random variations. Okay, there are three samples having the random variation. So what actually the random variation is? You can see here the normal distribution. Okay, resulting from a variety of samples like sample 1, sample 2, and sample 3 here in this particular example. And it is taken from the same population over time. So from the same population, these three samples has been collected, and these samples have some normal distribution. You can see on the screen in figure 12.1. So we find a consistency in the amount of dispersion. You can see here, the amount of dispersion is consistent. You can see that there, you can see the distance between the mean and this extreme point is same to the distance between this mean and this extreme point in sample 2, and similarly in sample 3. So you can see that the normal distribution in these three samples are the same. They are consistent. So the dispersion from the mean is actually the same in all the three samples. Okay. Okay. The fact that not all the observations within the distribution fall exactly on the a target line. um, it shows that there is some variation. Okay, there is some variation. However, the consistency of the variation shows that only the random causes of variation are present within the process. So within the process there are only the random variation that are present. So this means that in the future, when we gather sample from the process, we can expect that the distributions associated with such samples also will take the same form, like like these samples. Okay, let's discuss the non-random variation, and then we will move toward the the example of non-random variation as well. When we discuss the non-random variation, in that case you will um, more clearly understand the random variation, the non-random variation, and the differences between these two types of variations. A non-random variation is, we call it the special cause variation as well. So non-random or special cause variation result from some event. The event may be a shift in a process mean or some unexpected occurrences. Okay, um, for example, we might receive flawed materials from a supplier. For example, we have received we might receive a material which has some flaws, okay, or few flaws, and we are getting that material from a supplier. For example, we got it from the supplier. There might be a change in work shift. An employee might come to work under the influence of drugs or some depression and make errors. The machine may break or not function properly. Okay, so just I'm giving you an example of which is completely related to this particular figure. Again, please listen to my example. For example, the example for the non-random variation is, for example, uh, we might receive a flawed materials from a supplier, and there might be a change in work shift. Okay. Uh, for example, this sample is produced, uh, in a good conditions, for example, and this is and this sample is produce a flawed machine or a breakdown machine, or an equipment which has some errors or problems, and this sample has been collected from uh, any other equipment that have again some problems, okay, software related problem, for example. Okay, so these samples are different. Okay, uh, so these samples are different, for example, because there an employee might come to work under the influence of drugs and make errors, for example, while producing this sample, and another employee has some he didn't sleep well last night, for example, so he is disturbed and he produced this sample. And this third sample is produced by another employee who caused the machine to break or not function properly. Okay, so this figure shows the distribution resulting from a number of samples taken from same population over time with non-random variation. So you can see here the non-random variation. Okay, this is the random variation. Okay, and you can see the consistency in the dispersion here in all the three samples. But in non-random variation, you can see they are inconsistent. The dispersion are inconsistent and they are changing. So when we compare this figure to this random variation, it's clear that the non-random variation results in a process that is not repeatable. Okay. um, so I hope I have explained this particular topic as much as possible. Okay, let's discuss some other thing in statistical fundamentals. Okay, let's discuss the process stability first. Uh, process stability means The variation we observe in the process is random variation, that is the common cause, and non-random variation. Okay, so process stability means that the variation we observe in the process is random variation and not non-random variation. So to determine the process stability, we use process charts. Okay, to determine the process stability, we use process charts. Process charts are graphs designed to signal process workers when a non-random variation is occurring in a process. Okay, so we will discuss the process charts later. Let's discuss the sampling methods here. To ensure the processes are stable, data are gathered in samples. Process control requires that data be gathered in samples. For the most part, sampling methods have been preferred to the alternative of 100% inspection. The reason for sampling are well established. Samples are cheaper, take less time, they are less intrusive, and allow the user to frame the sample. In cases where quality testing is destructive, 100% inspection would be impossible and would literally drive the company out of business. In some processes, chemicals are used in testing or pull tests are applied to cables. So these destructive tests ruin the sample, but are useful to show that a good product is being made. Okay, yeah. Um, I hope you understood what I have talked to you. Um, let's discuss some sampling methods here. The first one is the random samples. Randomization is useful because it ensures independence among observations. To randomize means to sample in such a way that every piece of a product has an equal chance of being selected for inspection. This means that, for example, if 1,000 products are produced in a single day, each product has one out of 1,000 chance of being selected for inspection on that particular day. Random samples are often the preferred form of sampling and yet often the most difficult to achieve. This is especially true in process industries where multiple products are made by the same machines, workers, and processes in sequence. In this case, there is not independence among observations because the process results in ordered products that can be subject to machine drift. Another one is the systematic samples, as the name suggests, systematic. Okay, so let's talk about the systematic samples. Systematic samples have some of the benefits of random samples without the difficulty of randomization. Samples can be systematic according to time or according to sequence. If a sample is systematic according to time, a product is inspected at a regular interval of time. For example, say every 15 minutes. So after every 15 minutes, we will have to, sample or inspect a product. Okay. Systematic mean if the samples can be systematic according to time, then that means that the product is inspected after every 15 minutes. If a systematic sample is performed according to sequence, so that means one product is inspected every 10th iteration. Like one product is inspected after every 10th product. Okay. Okay, and the last one is the sampling by rational subgroup. So a rational subgroup is a group of data that is logically homogeneous. That is, Variation within these data can provide a yardstick for computing limits on the standard variation between subgroups. For example, in a hospital, it may not make sense to combine measurements such as body temperature or medication levels taken in the morning with measurements taken in the evening. Obviously, the body temperature or the measurement in the morning is different, or the medicines in the morning can be different than the body temperature or medicines at the evening. Okay, so morning measurements occur before medications are given and before the first meal of the day, and constitute a rational subgroup. Evening measurements, which is another subgroup, are taken after treatment has been provided during the day, medications have been administered, and patients have been nourished. If data are gathered that combine these two subgroups, for example, the night and day measurements, then differences between morning results and evening results will not be detected. If variation among different subgroup is not accounted for, then an unwanted source of non-random variation is being introduced. Okay? Okay. So I hope this was, simple one. Let's talk with process control charts. One of the most important topics, I would say, for the quality are the process control charts. Now that we have learned about variation, it is time to learn about the tools used to understand random and non-random variation. Statistical tools or statistical process control charts, we call it the process chart or control chart as well. These charts are the tools for monitoring process variation. Okay. You can see here a control chart in figure 12.3. And this shows that it has an upper limit. Upper limit, we call it the upper control limit. And the lower limit, we call it the lower control limit. And we have the center line here as well. We will discuss some control charts in the coming slides. So we will move toward those slides later. Let's discuss first the variables and attributes. What are actually variables and what are attributes? Please listen to my words and please try to know about the the difference between the variable and attribute which is presented on the screen as well. To select the proper process chart, we must differentiate between variables and attributes. As we already stated that a variable is a continuous measurement such as weight, height, or volume. So these are variables. What is attribute? An attribute is an either or situation. Example of attribute is, for example, the motor is either starting or not starting. Okay. Or the lens is either scratched or not. Okay. So these are actually attributes. So in this lecture, actually we are going to just discuss the variables. Okay, as the title is based on the variables. As the title of this chapter is based on the variable. So we will here discuss the variables and the variable charts and the charts for variables, and in the next lecture, inshallah, we will discuss the charts for the attributes as well. Okay, so the variable charts are X or X bar chart. The range chart, moving range chart, or standard deviation chart. Okay, so these are the charts that we can use for variables, for example, height or volume, etc., as we have discussed. And attribute for attributes, we can use the proportion defective P. Okay, proportion defective, or NP, number defective, or the number conforming, and the number non-conforming. So we will discuss the attribute chart in the next lecture, and we will discuss some of the charts like X bar chart and range chart, and with examples in this particular chapter or lecture. But before that, let's discuss some central requirements for properly using the process charts. You must, one of the requirement is that you must understand this generic process for implementing the process chart. Obviously, you should know what actually this process is, or this chart is. You must know how to interpret process chart. You need to know when different process charts are used, and you need to know how to compute limits for the different types of process charts. Okay, so these were some of the central requirements for the properly using process charts. Now let's discuss a generalized procedure or process for developing the process chart. That means that how to produce the process chart. So there are different process charts, but we can have a a generalized procedure for all of these charts. So let's discuss that particular generalized procedure for developing the process chart. The process for developing a process chart is the same for almost all charts. The only difference are in the actual statistical computations. So following are the steps that can be used in different developing the process control charts. The first one is identify the critical operations in the process where inspection might be needed. Obviously, you have to identify the critical operations in the process where you think that inspection is needed. So these are operations in which if the operation is performed improperly, the product will be negatively affected. Okay, so this is the first one. The second one is identify the critical product characteristics. The critical product characteristics. Okay, so the second step is we have to identify the critical product characteristics. These are the aspects of the product that will result in either good or poor functioning of the product. And the third one is determine whether the critical product characteristics is a variable or attribute, because we will use different process charts for variables and attributes, so we should know the differentiation between these two. Okay, and we should know whether the product characteristic is a variable or attribute. Okay, the fourth one is select the appropriate process control chart. Yes, after knowing whether the product characteristics are variable or attribute, based on that we will have to select the appropriate process control chart from among the many of types of the control charts. This decision process and the type of charts available will be discussed inshallah in the coming slides. The fifth step is establish the control limits, like we have discussed in the previous lecture, the upper control limit, lower control limit, and the central line. Okay, so you will have to establish the control limit and use the chart to continually monitor and improve. And the sixth and last step is to update the limits when changes have been made. Obviously, when you did some changes, then you will have to update the limits as well. Okay, let's discuss understanding the control charts, what actually control charts are, and then we will inshallah explain the X and R charts. Okay, understanding control chart. A process chart is nothing more than an application of hypothesis testing, where the null hypothesis is that the product meets requirement. Okay, obviously X bar chart is a variable chart that monitor average measurement. Okay. Control charts draw a sampling distribution rather than a population distribution. Obviously, you will have to take some samples from the population data. Okay. So we can, draw a control chart for those things as well. Control charts make use of the central limit theorem, which states that when we plot sample means, the sampling distribution approximates a normal distribution. Now, how to interpret the control charts? Please listen to these points attentively. The first one is, before introducing other types of the process charts, we discuss the interpretation of charts. The figures in the next several slides, inshallah, will show different signals for concerns that are sent by a control chart, as in the second and the third box. When a point is found to be outside the control limit, we call it out of the control situation. Okay, so I will discuss it in the coming slide. Just listen to these points, and inshallah then I will explain these points in the coming slides. When a process is out of control, the variation is probably no longer random. Okay. I will explain all those points here. Okay, just look at the first in figure 12.10 in front of you on the screen. You can see the control chart evidence for investigation, and I will explain the previous slides, the slide number 21 points here. Okay, I'm going to interpret the control chart here. In normal behavior, you can see here that we have the central line. The upper limit, we call it upper control limit, and the lower limit, LCL, we call it lower control limit. Okay, and this is the normal behavior. In this normal behavior, you can see that all the points are within the control limits. Okay, so the points that are very near to the central line are more, reliable, I would say, and the point that are far are less reliable, but within the control limits, mean the products or the process is or the processes, all these processes or the products are within the control, and they are acceptable. Now let's move toward the second part of the figure. Here you can see that one data point is out, it is above the upper control limit. So we will have to investigate for this poor performance, because that means that it is out of control. This point is out of the control limit. Okay, so that means that we have to investigate for the cause of poor performance. And after investigating and correcting that, we will try to push this point below this particular upper control limit line. In the third part of this figure, you can see that one point is below the lower control limit. So again, we can say that this point or this data or this process is out of control. So we will have to investigate for the cause of improvement. We will have to investigate the cause of poor performance here, but if it is below the line, then we will investigate for the cause of improvement. Okay, now let's move toward this part. Here you can see that the 2 points, they are near to the upper control limit, any beyond 2 standard deviation from the mean. From this mean, they are beyond 2 standard deviation. That means that we will have to investigate for the cause of poor performance. Okay, these points are within the control limit, but these points are near to each other. I mean, these 2 points are near to each other and to the upper control limit. So these points that means that the performance is poor here. Okay, let's move toward the next one, or the second last. Two data points are near to the lower control limit, and again these points are about two standard deviations away from this particular mean, this mean. Okay, so or central line. So we will have to investigate these points for the cause of improvement. Okay. Okay, and the last part of this, or the sixth part of this figure, shows that these five data are above the central line. So we will have to investigate for the cause of sustained poor performance. Okay, कि यहाँ पे पॉइंट्स ज्यादा करीब है, यहाँ पे भी ज्यादा, ये दो पॉइंट्स करीब थे, ये भी ज्यादा करीब थे, तो यहाँ पे मतलब कुछ एरर आ रहा है, मतलब ये ऊपर आ रहा, ऊपर जा रहा है. इट इज नॉट ऑन द सेंट्रल लाइन, इट इज above the central line. ठीक है, ठीक है, within the limits तो है, these points are within the limits, but okay, these are near to each other. So that means that not just a single or two points are above these lines, or far from these lines, but four points are above these particular this particular line. So we will have to investigate for cause of sustained poor performance. Okay, look into this part of figure 12.10. The 5 points are below the central line. So we will have to investigate for the cause of below mean performance. Why these points are below? Of these 5 points are, throughout these points, 5 points are below this particular central line. Why? So we will have to investigate for that. Okay. And that is actually this is the reason of the the main purpose of the process control chart. It will help us to know which data, or which process, or which part is out of control, or near to the upper or lower control limits, and why. Okay, so we will have to investigate for that. Okay, 7 successive points you can see here on increasing or decreasing line. So we will investigate for the progressive change, why it is, why there is a certain change from, after this particular point. Okay, so you can see here that these 7 points are, increasing, and after on increasing line, and after that, that is, rapidly decreased. Okay, those points are rapidly decreased here. Okay, erratic behavior investigate. So you can see the erratic behavior. Okay, this is obviously, yes, erratic behavior. Okay, so we will have to investigate it as well. And the sudden change in level. Okay, yes, you can see the level of this point is suddenly changed to this point. Okay, suddenly it is changed, to this point, from the near to the second standard deviation, I think, of this point. The point is directly moved to no, move below the center line. Okay, up to around these 2 standard deviations. Yeah, so we will have to investigate the sudden change in the level. So then, the purpose of these slides were just to interpret the control charts for you. I hope you understood these charts. If not, then you can repeat, you can listen to my this lecture repeatedly. That may help you to understand these particular parts of the figure. Okay, now it's time to be again very attentive, because we are going to discuss the X bar in our charts, and these charts are extremely important. These are actually the process charts. Okay, and these X bar and R charts, as we have discussed in the previous lecture, that these are charts are used for variables. Along with these charts, we can use the S chart or the moving average chart as well, but we will not consider those charts here. We will consider just X bar and R charts here for variables in this particular lecture. So please listen to these charts, because we will solve an example for X bar and R chart as well. Okay, So the X bar chart is a process chart which is used to monitor the average of the characteristics being measured. To set up an X bar chart, select samples from the process. For the characteristics being measured, जो आपने measure करना है, you will have to select sample from the process for the characteristics that you want for to be measured. Then form the samples into rational subgroups. Okay, you will have to form the samples into rational subgroups. Okay, I will explain these points inshallah in the coming example. So just listen to me right now, and inshallah then I will explain these points directly or indirectly in my example, and you will understand it very easily. Next, find the average value of each sample by dividing the sums of the measurements by the sample size and plot the value on the process control X bar chart. Okay, the R chart, that was actually about X bar chart. Now let's talk about the R chart. R chart is used to monitor the dispersion of the process, and it is used in conjunction with the X bar chart when the process chart is a variable. To develop an R chart, collect samples from the process and organize them into subgroups, usually of 3 to 6 items. Okay. Next, compute the range by taking the difference. Range किस तरह find होता है? We can find out or compute the range by subtracting the lowest value from the highest value within a particular subgroup. Okay, and then plot the R values on the R chart. Okay, so I would like to explain X bar chart and R chart here in this example. Okay, and this example is used for constructing the X bar chart. How to construct X bar chart? Okay, so the statement of example is: a quality control inspector at the Cocoa Fizz soft drink company has taken 3 samples. Point to be noted. Okay, 3 samples with 4 observations. Please note these points. A quality control inspector at the Cocoa Fizz Okay, again, a quality control inspector at the Cocoa Fizz soft drink company has taken 3 samples with 4 observations. 4 observations. Sorry, I didn't highlight it, but it is important. 4 observations, each of the volume of bottles filled. If the standard deviation of the bottling operation is 0.2 ounces, use the data below, this data I am talking about, to develop control charts with limits of 3 standard deviation for the 16 ounces bottling operation. So the 4 observation 1, 2, 3, 4 is actually the sample size. Okay, so here the observations, number of observations are 4, and these 4 observations are actually the sample size. Okay, the first step is to calculate the mean of each sample. Okay, so we have 2 methods that can be used for finding out the making the control charts. Okay, we will discuss each of them one by one. Okay, let's talk about the first one. For the first one, the step 1 is to calculate the mean of each sample. Mean means the average of each sample. So here for column 1, okay, what this table represent? This table represent that for observation 1 at time 1 the value was 15.8. For observation 1 at time 2 we had the value of 16.1, and for observation 1 and time 3 we have value of 16.0, and similar for is the case for 2, 3, and 4 observation. Okay, so this in the first step we have to find out the mean X bar. Mean A for us mean is actually the x bar. So how to take mean? Mean is summation of these of the first column divided by the number of values. So the mean for the first column would be 15.8 plus 16.0 plus 15.8 plus 15.9 divided by number of samples, which is 4. 1 2 3 4. So and that would be equal to 15.875. Similarly, we can take the mean of time of this second column and the mean of the third column. Okay, so these are the means, and means are actually the x bar. Okay, x bar is actually the mean. In step 2, we have to identify the standard deviation of sample mean. The standard deviation of sample mean, the standard deviation was given, which was 0.2. But we have to find out the standard deviation of the mean, which is sigma x bar. So that is equal to, the formula for sigma x bar is sigma divided by under the root sample size. N is actually the sample size. So 0.2 divided by 4. Sample size is 4. Observation 1, 2, 3, 4. These are the 4 observations, which means 4 sample size. So N is 4. So this would be equal to 0.1. Okay. Now the third step is to find out the center line. Okay, and the upper control limit and lower control limits. Okay, so the central line here for x bar chart, for please listen to me attentively. The center line for x bar chart would be x double bar. X double bar is actually the average of x bar. So average of the values of x bar, like this, which is 15.875 plus 15.975 plus 15.9. Okay, these are the x bars. So this plus this divided by 1 2 3 3. So that would be the mean of x bar. So the mean of x bar is actually x double bar. Okay, which is equal to 15.92. So x double bar is actually the center line of the process chart. Okay, now let's move toward the upper and lower control limits. For upper and lower control limit, as you know that here the standard deviation is given. The z value in the question is given, which is 3. You can see here. Okay, use the data below to develop control chart with limits of 3 standard deviations for 16 ounces. So the standard deviation is given, which is 3. Okay. So if z is given, okay, if the standard deviation is given, then you can use this formula. Okay. For upper and lower control limits, we can use these formulas if z is given. Okay, if the standard deviation value is given. So as it is given in the question, so therefore we can find it very easily, like a UCL, upper control limit for x bar chart would be x double bar, which is this, plus z, which is 3, or standard deviation, into x bar. We have found it in this slide. You can see it is as sigma divided by under the root n. N is the what? N is the sample size. So this would be equal to 0.1. Okay. So now put the values here in this expression, which is x double bar, which is 15.92, plus z value is 3, which is the standard deviation, into x bar. Okay. So this is the sample mean standard deviation. So when we put the values here, and then we will get the values of 16.22 for upper control limit and 15.62 for the lower control limits. Okay. Now the next step is to draw the chart. Like this center line is x double bar. Okay, which is 15.92. Okay, 15.92. Now this is the upper control limit, which was 16.22. Oops. Okay, 16.22 should be the upper control limit, and the lower control limit should be sorry, 15.62. Okay, so these can be these can be the upper and lower control limits. What are actually these points or represent? These points are actually the values, the data. These are the points you can see here on the table. So there may be a little bit, a difference in this table, but actually I want to explain this whole process to you and explain how to construct the process chart. Okay, so you have to understand how to construct the process chart from these steps. Okay, now another method is for the X bar chart using R bar. We have to use the R bar and A2 factor. Okay, if standard deviation is given, then we can use these formulas. It's okay. Okay, as you know that in the question, the standard deviation was given, which was 3. So we can use this formula. But if the standard deviation is not given, then what we can do? We need to use this method. Okay, and in this method we will use the R bar and A2 factor. And for that we have a table. Okay, we have a factor table. Okay, now for the second method, step 1 is to calculate the range. So what is range? Range mean highest value minus lowest value. So the highest value in this column is 16.0, and the lowest or the minimum value is 15.8. Okay, so 16.0 minus 15.8, its range would be 0.2. Similarly, the maximum value here in this column is 16.1 and the minimum one is 15.8. So 16.1 minus 15.8 would be equal to 0.3, and similar for this. Okay, now if you want to find the R bar, so R bar is actually the mean of R. So this plus this divided by number of values. So 1 2 3, so 3. Okay, so its R bar would be 0.233. Okay, so you have to remember this value. The R bar value is 0.233. For R chart, as you know, for X bar chart, the center line is X bar, but for our chart, the center line would be R bar. Okay, now let's move toward the second step, and which is to calculate the center line, upper control limit and lower control limit. So the center line is same for X bar chart. It's the center line would be X double bar. Okay, which we have already calculated in the previous slides, which was 15.92. But we can use the different values here, because if the standard deviation is not given, then what we can do, we will have to use the A2R formula for UCL. So how can we find the A2R? Okay, we can find it from our sample size. As you know, in the question, the sample size given was 4. 4 observations were actually the sample size. So we will go to the 4, which is this, our sample size is 4. Okay, now in front of 4 we have to find out the value A2, which is 0.73. Okay, so X bar is this plus, okay, A2 we got it from the table, which was 0.73, multiply with R bar, which we have already found in the previous slide, which was 0.233. So we will put it here, and our value is 16.094 upper control limit, and for lower control limit its value is 15.75. Okay, now if you want to find the R, so using these values you can draw again the X bar chart. Okay, now if you want to find to draw the R bar chart, then what we can do, we will have to use R bar as a center line. Okay, we have already defined it, but its values is different for R chart. Okay, UCL formula and LCL formula are different for the R bar chart. UCL formula is D4R. Okay, so again how can we have the value of r, which is 0.233, but we don't have d4 available in the statement of the question. So how can we find it out? So we can find out it from table using the sample size, and our sample size in the question was, which was given, was 4. So in front of 4, the value of d3 is d4 is 2.28. So d4 is 2.28 multiplied with r bar, which is 0.233, so its value is 0.53. And for LCL, the value of d3 in front of 4 is 0.00, mean 0. So 0 into 0.233, which is equal to 0. Okay, so this is the R bar chart. This is the R bar chart. Okay, this is the R bar. Value of R bar is actually the center line, and this is the upper control limit, which was D4 R bar, and it is the lower control limit, which was 0, and it is equal to D3 R bar. Okay, and these values actually represent the data which was given here. Okay, this is the data which is plotted here on the table. Okay, now let's quickly talk about application of the process out of control. If the values are out of the control, okay, for example, if this point is for example, it is out of the control limit, and for example, if it is located here, okay, look into the cursor please. If it is located here, then we can call it that this point is out of the control, or this data is out of the control. We have to do something to put move back into the within the control limits. So what we can do is, if a process loses if a process loses control and becomes non-random, the process should be stopped immediately. We have to stop the process immediately when we find out that any process is out of the control. Okay, now in many modern process industries where just in time, or JIT, is inventory is used, this will result in the stoppage of several workstations. Obviously, this will stop the several workstation, because in just in time we don't have the inventory. Okay, so the team of the worker who are to address the problem should use a structured problem solving process. Yes, obviously. Now this is you can see here is the X bar or S chart. Okay, so I'm not going to discuss it here. Our objective for this section was to just discuss the X bar and R bar chart here, but you can do it on yourself as well, and I will actually, if you can't do it on yourself, then don't worry, I will explain the remaining charts for variables at the end of our course. Okay, so at the end of our course we will have a 1 or 2 lectures in which we will discuss these different types of charts for variables and for attributes respectively. Okay, some control charts concept for variables. Okay, now choosing the correct variable control chart. Which control chart you should use? So for that you have to visit figure 12.18 in the textbook, total quality management, by Thomas Foster. Okay, so in that book, in chapter number 12, you can find out the figure 12.18, and you will be able to know which control chart is most suitable for a particular variable. And corrective action. Okay, if when a process is out of control, obviously we need to correct it. Okay, we need to make it within the control process. Okay, so corrective action steps are similar to continuous improvement process. Corrective action steps are like the first thing that you should do is to carefully identify the problem. Okay, then form the correct team to evaluate and solve the problem. Use the structured brainstorming along with fishbone diagram and affinity diagram that we have studied in the previous lectures. Brainstorm to identify potential solutions to problems. Eliminate the cause of the problem. Okay, eliminate the cause of out of the control process. um, then restart the process and document the problem, root causes and solutions. Now communicate the results to of the process to all personnel so that this process becomes reinforced and ingrained in the organization. So how do we use control charts to continuously improve? One of the main objectives of the control chart user is to reduce the variation. Okay, and how can you reduce the variation? Okay, when the upper and lower control limits gets closer together, then that means that the process is improving. Okay, so what we need to do is to move the upper and lower control limits closer towards one another. Okay, um, two key concepts here are that the focus of control chart should be on continuous improvement. Obviously we are doing obviously this for improving the um, quality. Okay, and the second one is control chart limit should be updated only when there is a change to the process. Otherwise any changes are unexpected. Okay, in some cases some of the people do some tampering with the process, which is not a good thing, which is bait, obviously. So one of the cardinal rule of process chart is that you should never tamper with the process. You should never tamper with the process for, when you know that, okay, the process is going outside of the control limit, then what you should do is to not tamper with the process. You should stop the process immediately, and you will have to take the corrective actions. Okay, and you might wonder, why don't we make adjustment to the process anytime the process deviates from the target? So the main reason for that is that random effects are just random. So this means that these effects cannot be controlled, or these effects can be uncontrollable. So if we make adjustment to a random process, we actually inject a non-random activity into the process. Okay, so that was the end of this lecture. Thank you so much for being with me. And uh, for more details and for more videos and lectures regarding different courses, I will recommend you to please subscribe my YouTube channel by clicking this link here, or and like my Facebook page as well. And the name of the YouTube channel and the Facebook page is Learn with Wasim. Okay, but if you have any question regarding any of my lectures, you can please feel free to contact me on my email, which is learnwithwasim@gmail.com. Thank you so much again. Bye bye.